So now let's treat those important examples. All right, let's take a new page. All right. So first one, we want to, we are in Rn and we are looking at the dot product. Okay, so that in Rn, how do we define the dot product? So it means that we have X, which is given by X1, X2, its n components, and we have Y that is given by its Y components, and we define the dot products of X times Y. So again, so that's the dot product, but the notation I'm going to use for an inner product is going to be something like this, right? As the sum of xi, yi for I equals to 1 to n. Okay, that's the usual dot product that you know how to work with. Another way to write this is using the vector notations. It's going to be well, actually, these should be um, column vectors. So one way to define that is that it's going to be yt times x. Okay, so the three, I remind you, the three things we have to show: that it's symmetric, that it's bilinear, and that it's positive definite. All right, so symmetric. Obviously, we have that x, y is equal to yx. Why is that true? Because if I use that definition of the dot product, xy is going to be equal to sum of xi, yi, while yx is going to be sum of yixi from 1 to n, from 1 to n on both, and of course both are equal to each other. So we have the symmetry. Now, do I have bilinearity? So how do I do that? Let's take lambda in R. Let's take x1 in Rn, x2 in Rn, and y in Rn. So do we have that lambda x1 plus x2y is equal, so that's the question we have to answer. Do we have that it's equal to lambda x1 y plus x2 y, and even that it's equal to, again, a question, to lambda times x1 y plus x2 y. Okay, so let's do this. Oof, sorry about that. Okay, sorry about that. So, do we have bilinearity? Okay, so let's go back here. So maybe we should give some names here. So x1 is going to have components x11, x12, x13, etc. up to x1n. Okay, and that should be the column vector. And x2 should be x21, x22, x23, etc. up to x2n. Okay, you can come up with a better notation if you like, but that's the one that I came with. All right, so now if I take lambda x1 plus x2, this is going to be the item from Rn that has x11 plus, sorry, lambda x11 plus x1 x21, lambda x12 plus x22, lambda x13 plus x23, etc. Lambda last component would be lambda x1n plus x2n. Okay, so Now if I take the dot product of lambda x1 plus x2 with y, with some y, same definition as before, it should be the sum from I is equal to 1 to n of lambda x1i plus x2i, that's the ith component of this vector, times yi. Okay, that's an I. Maybe I should make it better. That's an I here. Okay, so that's the definition of my dot product. So, but the thing is that this sum is linear, so I can really rewrite that. I can go a bit faster. I can really rewrite this as lambda sum on I of x1i yi plus sum of x2i yi. Okay, from 1 to n, and I really have that it's lambda x1 with y plus x2 with y. Okay, or you could use the fact that lambda x1 plus x2 with y could be described as y transposed product with a lambda x1 plus x2, and use this linearity. Well, it's nothing new, yt times x1 plus yt times x2. Okay, right, so and you got the same result. So we've got linear for the first argument. We also had that it's symmetric. So look at this reasoning. If I want to show linearity in the second argument, what would that be? I would like to show I've got x, I've got lambda, y1 plus y2, and I would like to show that it's linear in the second argument. So I would like to show that it's x times lambda y1, so I would get lambda y1 plus x product with y2. How can I show it using those first two properties that we proved? But well, we can use symmetric, the symmetric properties, so we get that it's indeed equal to lambda y1 plus y2 x. Okay, I'm using the symmetric property. I can exchange the rules of the x and y's. And then I can use the linearity for the first argument that it's going, and that tells me that this is, so I already proved linearity in the first argument, so that would be y1x plus y2x, and then use symmetry again by saying it's lambda x y1 plus x y2, and that's it, it's proved. All right, so I've got linearity for on one of the arguments plus symmetricity. It means that it's bilinear and symmetric, of course. Now, finally, we have to show positive definiteness. So what does it mean? It means that if I take twice the same argument, x and x, do we have that it's greater or equal to 0? And so first thing, that there are two parts to this. One, we have to show that it's greater or equal to 0. Secondly, we have to show that if ever that is equal to 0, it implies that x was actually the 0 element. Okay, so first of all, let's try that. X scalar product with itself is going to be the sum of xi squared for I equals 1 to n. And of course, this is a sum of squares, so it's greater or equal to 0. So the first part of the positive definiteness is no problem. Then what comes next? If assuming that is equal to 0, does it imply that x is equal to the 0 of Rn? Okay, so let's try. X with x, that gives you sum of xi squared. assuming that it's equal to 0, of course, the sum of positive items equal to 0 implies that all these items have to be equal to 0. So that x is equal to 0 of Rn, the item of Rn that has 0 components everywhere. Okay, so I gave a lot of details for this first um, product, this first scalar product. This one you already know how to work with it, but you see that these are the exactly the three properties we want to show on all the other examples.